ready to start. All right, then I will take up, let's see, the last thing we did, we were doing collisions on the air track here with momentum. Tidy up momentum, chapter 6, and get into chapter 7 today. Did you get this number okay? So, work through a little more of these collisions. Some of you probably have never done it. We had elastic collisions where they bounce. So, yeah, that's obvious enough. It's the inelastic that sticks or combines. What was that? Oh. Such as football players tackling each other and they stay together. Or a car runs into a wall and it crumples, or two cars, but they're kind of together afterwards. A fish swallowing a smaller fish, because afterwards they're together. Those are inelastic. For these, momentum's conserved. I told you total momentum is always conserved. So whatever the total momentum was before the collision happens, and again, a collision can be them coming together. It can also be them separating, as we saw. Whatever it was in the initial state, the total momentum will be that always. To emphasize with those carts, started out with total momentum of 0. So then I burnt the string and the spring pushed them apart. They're both moving now. This one has momentum, this one has momentum, but the total momentum is still 0 because they're in opposite directions. MV positive, MV negative. They bounce, they come back, there's still total momentum 0, even though they've changed their momentum, the direction, and then they hit each other. And when the ones that had Velcro stuck, well, once they stuck, they stopped. And the total momentum is still 0. Then I did an inelastic with different masses. And I wanted to write that one out. I don't remember how I did this. Let's see. I think I had a big one coming in with some velocity, hitting a smaller one that wasn't moving initially. And even had I not shown you, I think your gut would have been right. We saw that they went off together with some final velocity. And you noticed right at the end, how did this velocity compare to this velocity? Anybody remember? If not, what do you think happens? Hey, most of you are here. Come on. You come in with a certain speed, hit something that's at rest, they stick together and head off that way. Will they head off at the same speed this one came in at? Slower or faster? Are your options slower? You're right. Now, how do we figure this out? That's what I wanted to write down. So we play that same game. The total momentum before has to equal the total momentum after. So I'll just start putting them down. Let's see. This guy has momentum m1 v1 plus m2 v2. And that has to equal m1 v1 final plus m2 v2 final. They could have changed their velocities. I kind of write it out generically first so I don't forget anything. Then you can start realizing this is 0, so that momentum goes to 0. What started as 0. So the big cart had all the momentum to begin with. Then this is an inelastic collision. They stick together, so this is really the total mass It's like one big block now, moving together. They both have the same velocity. That we'll just call it v final, as I drew up here. Because they're moving at the same speed, they're just different masses. This comes down. So there's our equation we can work with. So if any of these problems give you numbers that you need to compute, there you go. Conceptually, though, if he started out with all the momentum, afterwards, here's all the momentum, but it's split between the two, but they're moving together. So what did the mass do? How did it change? It went up. So the velocity is going to have to go down, as you guys predicted. So see, usually science agrees with your gut. And where we have problems is when our misconceptions is when it's non-intuitive. But this is one I like. Makes sense. At least, I hope it does. You'll tell me if it doesn't, right? That's why we're here. Well, let's put in some numbers. Let's say the initial M1 is 100 grams. And let's say M2 is half that, 50 grams. Let's say we're moving initially at 10 meters per second coming in. We weren't going that fast, but that's all right. These are just numbers. So could you figure out what that final velocity is? I hope so. Because I've given you everything but that value. If we just put them in, let's see. We got 100 times 10. So we start out with 1,000 units of momentum. Afterwards, we have 100 grams plus 50 grams moving at something. That's what we don't know. So 150 VF. So VF is 1,000 divided by 150. Factor of 10. Factor 2, 50. No, 15 goes into 100. Oh, thanks. Meters per second. Now, this is one where my gut, just if my initial knee-jerk reaction is, oh, the mass is half the size of the first one. So the velocity is going to go down by a half. Since the mass goes up, when we know the velocity goes down, my knee-jerk reaction is, oh, it's a factor of 2, so the velocity is going to change by a factor of 2. No, it doesn't work. Because the mass didn't change by a factor of 2. They're different by a factor of 2, but it didn't change by a factor of 2. Do you see that? It went from 100 to 150. That's not a factor of 2. The factor that did change from 100 to 150, a third. It went up a third, so the velocity went down a third. That worked. So you can play it conceptually, but sometimes you don't see that. So when in doubt, you just start. Conservation of momentum. The total before is total after. Write them all down, and you can figure things out. And then think about your answer. When you get an answer, does it make sense? If we had gotten this to be 66.7, maybe we just did a factor of 10 error or something. Or 66. Whoa, it's going, let me see, that's going 6 times faster. Where'd that energy come from? Maybe it's a clue something went wrong. If you haven't noticed yet on some of the homework, it asks you some of these things. You can reason through them conceptually, but sometimes doing this actually helps me conceptually, even though it's quantitative. Likewise, in Chapter 7, we're going to have conservation of energy. And you play the exact same game. So that's why I'm making sure you can see this. Any questions about the procedure? What if we switched? Let's do that one. What if we have the little one come in with a certain velocity and runs into a bigger one that's not moving? What'll happen? I didn't do that on the air track, so you can't like revert back to life experience. They're going to stick together. We'll make it inelastic. What do you think will happen? What's your gut tell you? Really slow down. Any other votes? Well, who's all gearing up for another big long? Oh, watch this. Total momentum before has to equal total momentum after. M1 plus M2, blah, 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 blah. Now it's just the other one that's 0. So this would be M2 V2. But they still combine afterwards. So it's the exact same thing. You'd still plug in the numbers and you would just get a different value, obviously. Because instead of this being M1 and V1, it'd be M2 and V2. This would be the 50, but together they'd be 150. So you can see, yeah, the mass goes up 2/3, so the velocity should go down 2/3. I don't even have to calculate it now. I know the answer. But in case you don't, there you go. Did you follow that? I know I talked it through because it's the same thing. What if it, yes? Oh. I, in my head, was trying to keep 2 with the same cart. It's now the one moving instead of the initial one coming in, which is now what I would normally have done, setting it up, so that we didn't get confused by switching carts, but it failed because it's still... So yeah, I was just taking the small one, which was the small one before, and kept it as 2. Sorry. And then covered it up so you couldn't refer back to it. What if it was elastic? And they bounced off each other. This case, but we made it elastic. What do you think will happen? They're going to bounce off of each other. Will one stop?
Which one's, so M2 is colliding with M1?
Yeah, this case. The smaller one's running into the bigger one. Let's see. Let's go maybe easier. Okay, this is coming in. It's got some momentum. This guy has no momentum. So the total momentum is initially all here. That part you can see. We just reason through this. Let's see. If this bumps into this one, my gut says this one's probably going to start moving that way. I don't know how fast, but it's going to start moving that way. Since it's bigger than this one, it probably won't be moving as fast as this one came in, but it'll be moving that way. You're probably still good with me, right? Agree with me? But what will happen to this guy? It might be a little more confusing. Is he going to keep going? Will he stop? Or will he bounce back that way?
It'll bounce back, slower.
Bounce back, but go slower. If it is bouncing back, I hope it slows down, because he just transferred some of his momentum to this cart. And since total has to stay the same, if he bounces back, he can't bounce back quite as fast. This is one where I think it's, well, I was going to use the word fun. You guys might not think it's fun, but I do now. Where I don't know what's going to happen. So we could do an experiment. That'd be easy. But I didn't pull the air track out. Or you can do that game again, and the math actually tells you what happens. Let's see, we got 50 grams going at, let's say, the 10 meters per second, plus the 100 grams moving at 0. Afterwards, we have 50 grams again moving at some velocity, m2 final. We don't know that. Plus 100 grams moving with some final velocity also. So this goes to 0. That's nice. We know what we start with, 500 units. So we're getting closer. We could figure this out and this out if we knew one of them. At this point, we don't. If I gave you the problem, of course, I'd give you one of those. But we can see that if this cart is going to move to the right any at all, because it gets bumped into, this will be positive. And this could go either way. So this is your teaser. When you start using conservation of energy, you can play the same game. And I won't make you do this unless you're fretting right now. But it is just algebra, but it's a system of equations. Who remembers that from algebra? You'll get a second equation, just like this one, but a little different in terms of energy, and it'll have two unknowns, the same two unknowns. Conservation of energy go well together. Now, with these mass ratios, my guess is this one's going to bounce back a little bit slow, like your guy was telling you. But it depends on the mass ratio sometimes. If this was a lot less massive, let's say this is just a little bit less massive. More massive, a little more massive than this one. You could certainly run into it and maybe kind of keep going. But there's going to be a cutoff there. Most likely it's hitting something heavier and it's bounced back a little bit. Okay. Clickers then. And I got some questions to see if this is making sense. So let's check. Just two questions. Pull your device out and log in. Continues on. Right after lunch meeting, right after he eats the little bit. What type of collision is this? Inelastic, good, because they're together afterwards. The little fish is now part of the big fish. Everybody had a chance to log in? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, large majority B. Less than before. Good. A little better. Opens are 10%, so here's the explanation. The big fish, what happened to its mass? It got bigger because it just ate a small fish. The mass has gone up. So what does its speed have to do? Slow down to keep the total momentum the same. Questions? Then, let's look at just the momentum of the big fish. Same scenario, I'm just asking you about its momentum now instead of speed. Little tricky.
Is the small fish considered an external force in this case?
It's part of the system. The little fish is part of the system. And actually, after lunch, it's part of the big fish.
Okay.
And like every other time I read this question, the author of the textbook made this one up. I'm always thinking, maybe you should have it slightly different. So my little, what's confusing me, what bugs me anyway, I'll give you lessons bugging you too. After lunch, in real life, all that's left is the big fish. Because the small fish is part of the big fish now. I guess most of you are voted. I didn't see you change anything. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Used to be A. Oops. You're right. Momentum before the collision. The big fish. So the total momentum before was all in the big fish. The total momentum afterwards is the big fish, because the small fish became part of the big fish. It's not like they're just stuck together, moving together. So again, since the big fish's mass went up, the speed went down, the total momentum stayed the same. But all the momentum started with the big fish, and it all ended with the big fish. So his momentum stayed the same. Because that is where all the momentum is. Because he ate the little fish. Does that help those that missed it? Okay. Your pre-lecture questions. By the way, I know I didn't go over the last two because I looked at the responses and it was nearly 100% of the class got 100% of the problem, so I didn't figure you guys had questions. But if I ever fail in your mind to cover a pre-lecture question in that lecture, do call me on it. Let me know. Hopefully it's not because I just forgot. These are the two for today. The first one. When you say momentum is conserved, you mean that, and there are four options. The answer was this first one. When external impulses do not occur, a system's momentum remains the same before and after an interaction. My first tip-off is, well, that's the one that sounds the fanciest. Must be right? That's exactly how your author defines it, and that is technically correct. In my mind, I've been telling you, total momentum's always conserved. And I've been emphasizing that because if you include everything, you don't have to worry about this external impulses. In other physics classes, I mentioned this when I first started defining it. They kind of, I don't know, some of them probably don't prefer the way I say it. But if you include everything, it's true. It's just easier to remember, more conceptual. The idea being, yeah, if you treated the little fish as an external impulse, well then somehow all of a sudden total momentum doesn't seem to stay conserved. Or I should say momentum. Well, why do I want to nitpick whether it's an external force? Let's define our system. It's the big fish and the little fish. They both start out with momentum. They both end with momentum. Well, the little fish gets destroyed, but then it's always conserved. Well, if you look at the others, it's a teaching lesson. When two objects collide, the mass and velocity of each object will not change. Well, that doesn't seem to make sense. Or at least not always. Usually they change. When an impulse, excuse me, when an impulse acts on an object, its momentum will change. That's a true statement. Some of you might have chose that. Impulse is change in momentum. It requires an impulse. That's what causes the change in momentum. That's true. But we're asking about momentum being conserved. So it doesn't fit with this question. And the last one, momentum can be stored. I'm not exactly sure what that means, so that's not the right answer. You can say an object possesses momentum. It's coming in with so much momentum, and it can change. So it's like if you want to think of it as, because you have so much mass and you're going yay fast, you're storing momentum until some impulse comes along to change it. I guess that would be okay. The second one, well, I haven't taught you yet. This is my transition. When an increase in speed doubles the momentum, what happens to its kinetic energy? Who read ahead and knows the answer to this one? More than doubles? All right, let's turn the lights on and move to that. So kinetic energy is the energy associated, and many of you have probably been exposed to kinetic energy before, but it's the energy associated with motion. So if you're not moving, you have no kinetic energy. And it's 1/2 mass times velocity squared. And this is important. And for that pre-lecture question, if you double the speed, it's twice the velocity, then 2 squared is 4. You will have 4 times as much kinetic energy. So looking at momentum again, if you double the speed, it doubles the momentum. But it quadruples the kinetic energy. And this is kind of how it started. Historically, I won't go through it all, but what was her name? Émilie du Châtelet in the 1700s. She was like Galileo. And they had this question about, okay, our terms, momentum and kinetic energy. I don't know what they called it back then. Maybe oomph might make sense. It might be what we call it today if we didn't know what it was. They knew these objects possessed an oomph. You know, if you got hit by something, it hurt. It's like it possessed something. What is it? And there were arguments. There were debates over this. It was funny. Theoretically, they would talk and talk and talk. But then like Galileo, who just said, fine, let's just go do an experiment and find out. Let's put them on an air track here and do a collision. We'll know which way it goes. Hello? That's why I like Émilie du Châtelet. She did an experiment also. And basically, she found out that, hey, these objects come in with so much oomph, and the result is they seem to, how they move, how far they go, how big an indent it made when it landed or something. And the distance seemed to be proportional to v squared compared to v. So she just analyzed her data. I'll show you that. Here's some Hot Wheels cars. I'm going to pivot it here, put it back. The idea is I'm going to move this along. It's going to go in, and this is going to stop it. So it's like they're all moving at a certain speed. they break all of a sudden, and then they keep going because they have inertia. They'll have momentum, each of their masses. You probably can guess too, even though we didn't cover it, which one do you think will be moving faster as they rotate around? The outside, like on a merry-go-round. When you're on the outside, you're like, whoa! But if you're in the middle, you're like, whoop-de-doo. So yeah, this one will be going slower than this one, and faster yet. So this one will have more speed, more velocity. Let's just do it. So come in. They're stopped by this. And what slows them down? Friction. Friction is a force, and it's applied for a certain amount of time. So it applied an impulse to each of these cars and changed their momentum. You get an idea already. Lest you think it was a fluke, let's do it again. And she did something similar. I just thought this was a fun way to do it. Coming in, they break. And clearly, this one's going farther. Every time it goes farther. How about one more? So is this relationship linear? Or to the power, or to quadratic, to some power? And her experiments were better than this. I'll stop, because you guys get the idea. And if we did this over and over and over again and averaged the values, what I want to emphasize is this one went yay far. This one, which was twice as far away from the pivot, you can actually measure, was going twice as fast as this one. So this one had twice the speed of this one. Maybe it looks like it went twice the distance. It's kind of hard to tell. That's why you would repeat this. It's a little further. This one's 3 times. Maybe it went. But this one's way more. My bottom line is this, if you were to graph it, as the velocity increased, we could look at the distance they moved. And it's not straight. As you double the speed, it doesn't just double the distance. It seemed to be more like this, which was the squared factor. And that's how she figured out that this oomph that we end up calling energy is proportional to velocity squared. So they knew that kinetic energy was proportional to mass, because the more inertia it had, the more it would resist. She just narrowed down this part. So the obvious was, well, let's do this. And they probably tried that, but it didn't work out. They took data and realized there was a factor here. It's proportional to that. It exactly equaled that much. And empirically, just by taking a bunch of data over and over again, you can get this factor that stayed constant. There's other ways to derive this, but I don't think they're necessary. Similar to, remember we had the distance something moves was 1/2 a/t squared. That's what Galileo did. He noticed the distance things moved as they were accelerated down a ramp due to gravity. And the distance was proportional to time squared. It wasn't if you waited twice as long, it went twice as far? No, it went 4 times as far. And exactly how far it went, again, needed that factor. And it worked out perfectly. Does that help? So, one of the biggest lessons you can learn in Chapter 7 is energy is conserved, but also remember that kinetic energy is velocity squared. I ask you lots of questions about that. The other form is potential energy. And that's the energy associated with position. There are several types of potential energy in physics, actually. We're starting with gravitational. Gravitational potential energy. So I might just do PE, or if you prefer potential due to gravity, I don't care. So that is, this block, we would say, has 0 gravitational potential energy relative to the table because it has no height. It has no height. They put these together and realized it was proportional to mass, again, because of inertia. What's trying to pull it down? There must be some gravity in there, so acceleration due to gravity. And since I just told you it's associated with position, it depended on how high up it is. So there's your gravitational potential energy, and there was no need for a factor constant in that one. If I raise it up, we now say it has gravitational potential energy relative to the table. And this is because you can think of it as potential to do energy, to do work on something. If I let go of it, it falls. It picks up kinetic energy. And it can transfer that energy to the table. Well, where did it get that energy from? It was in it. People often say it stores gravitational potential energy, and that's fine to think of it that way. Let me ask you, though. No energy. Gravitational potential energy. Where did it get its gravitational potential energy? It doesn't just magically appear, because energy is conserved. I lifted it up. I exerted a force on it. What minimum force did I had to exert in order to lift it up? It's weight. Very good. So I exerted a force. We still have, here it's mg down. Earth's pulling on it. So I have to pull at least with F up. So if I can keep this moving at a constant velocity so it's not accelerating up, then the force I'm exerting on it while it's moving at a constant velocity is exactly its weight. Do you see that? Initially, I have to lift it a little more to get it moving, but very shortly. After that, though, as soon as I get it moving, or you could go really slowly if that helps you visualize, just as long as it's not accelerating, there's no net force, but my upward force is just countering its weight. And I apply that force. With momentum, we talked about how long we applied it. But in terms of time, how long? With energy, we talk about how long we apply a force, but how far, how long a distance. So I apply this force over a certain distance. That is another term, work. Force times distance. That's how we change energy. I like to think of work. There's another one. Don't think of objects as possessing work. They can possess kinetic energy. They can possess potential energy. I used to think of work as a form of energy. Now I don't. It's a way to transfer energy. So again, where did this get gravitational potential energy? Me. I did work on it. I changed its energy. And I did that by applying a force for a certain distance. You see the analogy where impulse is force for a time interval. In order to change someone's momentum, you got to apply an impulse, a force for a certain amount of time. To change someone's energy, you apply a force over a certain distance. The book talks about the work-energy theorem. Kinetic energy theorem. And that's just that work brings about a change in kinetic energy. I do work on this, I get it moving. While it's moving, it has kinetic energy. See, I jumped right to potential energy out here. Initially, though, I do work giving it kinetic energy, but then it stops. Now it's potential energy. You let go of it, it converts back into kinetic energy because it's moving. And no longer has potential energy because it's back on the table. So you've heard you can't create or destroy energy. Total energy is always conserved. That works too. Just like total momentum is always conserved, total energy is always conserved. It just changes forms, transfers into something else. These are just two of the forms, kinetic energy and potential energy. And how you get it to change and transfer is apply work, and you can get it to change. So back to this, these Hot Wheels. I do work on it. I apply a force to these cars over a certain distance. And see, it changes their kinetic energy. They now have no kinetic energy because they're not moving. They get moving, they have kinetic energy. Who has the most kinetic energy when it hits the block? The outside one, because it's moving the fastest. V. So this one's going to have the more kinetic energy. It'll be moving 4 times faster than this one. So how will the outside car's kinetic energy compare to this guy's kinetic energy? This one's moving 4 times faster than this one. Very good, because it's 4 squared. This has 16 times the energy than this one will. So, let's see. Whoa, that went crooked. So since he had 16 times as much energy to start with, it's going to take 16 times as much energy to stop it. That's why it'll generally go a lot further than just 4 times. And you get a curve instead of a straight line. And that's what Émilie du Châtelet discovered. But remember that. In the winter here with the ice, I know we're probably coming out of it, but if you go twice as fast on the highway, you think, oh, no problem. Slam on the brakes. What happens? You slide. The force of friction is going to act on you. Force of friction. Over a certain skidding distance, right? So you're applying a force. It's going to change your acceleration, your motion, over a certain distance. So friction is doing work on you in the car. That work is going to change your energy. The work kinetic energy theorem. It's going to slow you down, and all that kinetic energy you had is going to end up going away. Where does it go? If you end up stopped, it's no longer kinetic energy, but total energy is conserved. So where did that energy go? The brakes. You know, when you have friction, what happens? Yeah, you warm up. Heat is a form of energy. So it got transferred into heat, and it goes off into the atmosphere. So it's no longer kinetic energy in the car. It's heat in the atmosphere. So it does go somewhere, and you can know exactly how much heat you just produced. Because if you know how big the car is and how fast you were going, you know how much energy you had. And if all that goes away, and it's now in the form of heat, you know exactly how much heat you just produced. Because total energy is conserved. But back to, okay, you're going twice as fast. How far will you slide? I heard somebody. 4 times, 2 squared. Because you're going to have 4 times as much energy, so it'll take 4 times as much work, 4 times as much distance for the same braking force. Yeah. So just because you go a little faster on the highway, realize it'll take that much squared energy to slow you down and stop you. A lot of people forget that when they're cruising along. Speed doesn't kill, stopping does. All right, let's see here. Let's do a couple demos. Here we go. This ball can roll back and forth. Kind of mesmerizing. So I'm going to do work. Change this kinetic energy. It now has potential energy up here relative to the bottom here. I let go of it. Goes back and forth. Tell me, what forms of energy does it have right here? Potential. How about right here? Kinetic. How about right here? Sorry, what? Yeah, you're right. It's both. It plays this game. Potential at the top, potential at the top, kinetic down here. But as it goes down, it loses potential. So it has less potential. But it's moving now. It's going faster and faster because it's being accelerated down. So the kinetic energy increases. Here, we'll just do a plus sign. And over here, same thing. Here, it's got a little more potential and a little less kinetic. And here, it's got a little less potential and a lot more kinetic. The total energy stays the same. It just transfers back and forth. What's doing the work on this to change its energy? Gravity. It's the weight of the ball. What if I push this block up the incline? I'm doing a force over a distance. What did I just exert? Work. And it made it change its energy. I can do the same thing on this block. I lift it up. How much work did I just do? There's two ways to find out now. One, work is force times distance. If you knew the weight of this block, I exerted that amount of force for this distance, right? And you would know how much work I just did, right? There's another way. How high up is it? It's that same distance, I just moved it. If I knew its mass, I could figure out its potential energy, right? Where's that one at? Right here. Don't worry, I'll be done in 60 seconds. So if I plugged in its mass and gravity and that height, I would know how much potential energy it has. How much potential energy does it have? Well, it better be exactly how much work I just exerted on it, right? They should be equal. It's conserved. Did anybody notice this yet? If I apply the force of mg, its weight, and I apply that force for its height, that's the distance I move it, mgh. That's gravitational potential energy. It's the same formula. This work caused that change in energy. So you could figure that out with just force times distance or mgh, because they are exactly the same thing. Questions? All right, see you Friday.